Hello, and welcome back to the Unity Foundations tutorial. Today we will look at modular scene development with UI elements. We'll cover the uGUI system, canvas rendering, RectTransforms, and the Animator component and animation assets. Let's get started. Unity currently has two very different methods for building UI elements, the uGUI system and UI Toolkit. The uGUI system came first. It uses UI components and is integrated into your scene view. UI Toolkit is the newer system and has its own dedicated window. It works very similarly to HTML and CSS, with element tags, identifiers, and style sheets to define and style the interface. Today, we'll be using the uGUI system, which I still prefer because of the in-scene editing process, support for particle effects and custom shaders, and ability to work with Animator components and animation assets. Building on our previous examples, I have a blue cube scene, which represents our player, and a red cube scene, which represents our level. I can load either scene independently and have the output rendered through that scene's camera. If I load the levels together, I can use the priority in the camera settings to control which view is drawn on top. My level camera has a priority of -1, and my player camera has a priority of 0. So the player has a higher priority, is drawn second, and draws over the top of the red scene camera view, resulting in us only seeing the output from the blue scene camera view. I also still have our camera manager script attached to both cameras so that it turns off the level scene camera when the player camera is present, because we might as well not spend resources drawing a camera view we don't need. Now I'm going to add a Lives UI scene, which represents a gameplay HUD element. The canvas element in the Lives UI scene is currently set to render mode screen space overlay, which means it will render on top of all your content at screen level. It also means it always shows up in the scene view with its lower left corner at 0, 0, and uses the current game view pane as reference for how it sizes itself in your scene. Personally, I dislike that aspect of using a screen space camera. Having my UI in the scene view resize based on my application layout feels a bit weird to me. Instead, we can set our canvas render mode to screen space camera and assign a camera to render with. The camera still relies on the game view to determine its aspect ratios, but it no longer resizes itself with changes to the layout, because the canvas size in our scene is driven by the reference resolution and the camera, not the screen. This also means we can position our UI in the scene however we want by moving the camera. So if it's getting in the way, you can just move it to its own area or spin it around. You may have noticed that our game view is now drawing the UI scene render on top, and when we move the camera, we change the final render. Because this is a new camera in our loaded scene list, it's important to consider the competing camera issues we discussed last week. We want the UI scene camera to render our UI elements and only those elements. So we'll update the culling mask from everything to just the UI, which is the default for a canvas element. Now that the UI camera is rendering only our UI layer, we can't see any of the scene objects in the final render. To fix this, we'll adjust the environment type on our UI camera. By default, your camera will usually have a skybox or a solid blue color. These elements are essentially the background for your camera render. By setting this to uninitialized, we can tell the camera not to render any background. By default, Unity displays an uninitialized background in this bright yellow color as a sort of warning to tell you that there is no data set for the camera background. This is a newer issue that has cropped up in Unity 6 when using Universal Render Pipeline and render graphs. We can get around it by going to our Project Settings, then the Graphics tab, and scrolling down to the render graph options and turning on compatibility mode. Now our project runs as expected inside the Unity editor, and we're able to see the UI layer rendered above with a transparent background layer. And the player scene camera renders underneath. You may have noticed Unity warns us about our current setup and says that support for this mode will be removed in future versions. Whether that means the checkbox is disappearing entirely or that there will not be official support is hard to say. On the plus side, this will always continue to work in the current version of the Unity editor. We still have one more issue which we encounter when publishing our projects. If we build out and run as is, the published project does not draw the transparent camera background the way we want. One way to tackle this is by using a render texture, which is where we draw the individual camera renders to an image and then draw that composite image to the screen. The downside of this is that the render texture can be performance heavy and they can get a bit complex. Unity's own recommendation is to use camera stacking. Camera stacking is where you define one camera as your base and additional cameras are stacked on top. Unfortunately, it's not possible to use camera stacking in combination with modular scene development inside the Unity editor, because all cameras in a stack assigned via the inspector have to be in the same scene. You can see the camera in my other scene, even if I set it to an overlay camera, is not eligible to be added to the stack. However, once the application is running, this restriction can be bypassed, and we can create a camera stack using a script. This works out great because, as you may remember, your published application has to have a single entry point. This means that we can set up a base camera in that entry point, and then add any incoming cameras as overlays, while using the camera's priority setting to keep the stack in the proper order. This is the technique we'll use to get our application to output properly when compiled into a build. I have two scripts that I've written, a base camera and an overlay camera. The base camera script is placed on a new camera in our entry point scene. I've set this camera's culling mask to nothing because it isn't actually used to render anything in our game world. It's just used to collect the output of all of the other cameras. The overlay camera script goes on every other camera in our project that we want to be included in our render. If we look at the scripts, the overlay camera script essentially says, "Hi, I'm a new camera," whenever that camera is first instantiated into the scene. The base camera picks it up and adds it to the stack and says, "Okay, you're now an overlay camera and you belong in the stack based on your depth." When we run our project from the entry point, you can see that the active incoming cameras from the player and UI scenes have been added to the camera stack at their appropriate depths. The level camera was not added because the camera manager script ran its awake function first, deactivating the game object and preventing the overlay camera script from running its awake function. If we enable the red level camera manually, we can see it gets added to the camera stack at the bottom because of its -1 priority. And we're now seeing renders from the level camera and the player camera stacked on top of each other. When we build and run the project, we now get the desired result, and our player scene camera render is visible underneath our UI scene camera render. Now that we have a camera stacking solve in place for our production builds, we can continue to develop each UI system separately in its own scene module. We rely on the uninitialized render background only during the editing process, which allows us to combine any scenes we want in the editor simultaneously with easy edit access to those scenes and the ability to preview the final output in the game pane. Because the game view is composed of actual renders, the camera priority will dictate what appears on top in the game view. But the scene view will use the canvas's sorting layer and ordering layer to determine the appearance and what appears on top. So, double check these settings if you're seeing discrepancies between your scene view and your game view. Now each UI system can be easily confined to its own scene module, and because you can't use drag and drop across scenes, each system will remain truly modular, and it will become clear as to what dependencies your system actually has, what hooks you need to expose, and how best to accomplish that. A quick note on performance: running one extra screen render per canvas can eventually get expensive. With 20 simultaneous stacked canvas renders, I'm still getting around 60 frames per second when running the game in the editor, and that's including the editor's overhead costs, which means our final build will be even faster than that. If you run into performance problems due to stacking too many canvas renders, you can always turn your scene modules into prefabs, combine those prefabs into a single scene and a single render for your production build. Or you can do what I'm doing here and route all of your canvases to render through a single camera. And I'm getting around 60 FPS with over 100 stacked canvases. In terms of actually building your UI elements, the Canvas and RectTransforms systems allow you to mix and match percentage and absolute values to structure and position your interface elements. Every RectTransform is a bounding box, which can be divided into smaller child bounding boxes. These two can be divided into even smaller child bounding boxes. Each RectTransform is defined by its four corners in relation to the four corners, or anchors, of its parent element. The canvas is automatically sized to our screen and creates the first outermost rectangle. For each of its children, we define a percentage-based float value for the left, xmin, right, xmax, bottom, ymin, and top, ymax, where 0 is the leftmost edge of the parent, 1 is the rightmost edge, 0 is the bottommost edge, and 1 is the topmost edge. The bounding box for my bottom bar is currently set to match the leftmost edge, rightmost edge, and bottommost edge. The top edge is set to 0.15, or 15% of the way from the bottom to the top. After the anchor is established, you can use absolute pixel values to further adjust the edge of your box relative to the anchor. There are various layout components which can help you achieve different effects, such as the content fitter for shrink wrapping elements and the aspect ratio fitter for enforcing a specific aspect ratio. Individual UI components also have their own options which can determine appearance and layout. You can combine these components and options in different ways, allowing certain objects to collapse or expand and achieve whatever kind of layout you want. Unity's animation system is a powerful tool which can be used to add animations to your UI elements. It is possible to have one animation per game object and define all the animated properties for that object and all of its child components. However, often you will find that you are reusing the same animations for multiple UI elements, such as scale pulsing an element to get the player's attention, or transitioning it with a fade from 0 to 1 opacity. Each animation clip can affect multiple properties, but in order to be applied to different game objects, any objects wishing to use that clip must have the same properties as those being affected in the animation. In order to modularize our animation clip assets and keep them as reusable as possible, we will affect only the properties on the components of the root object. That way, this animation can be reused by any object with these components, regardless of its child structure. For example, we know that every game object has a RectTransform component, so animations affecting that component can be easily shared across all game objects. And the canvas group component can be added to any game object, and it controls the alpha for all child objects by setting an alpha value for the canvas group, thus making it another easy to share component for animation. The most straightforward way to add animations to a game object is to add the Animator component, which accepts an Animator Controller. An Animator Controller, accessible via your Animator window, is a sort of state machine which manages transitions between states. Each layer of the controller can only have one active state at a time, and each state can only have one animation clip. So, we will create one clip for each component or property that we want to edit, and one layer for each clip. Make sure you give each new layer a weight of 1, so that all layers will be played together. I'm currently using 2 animation clips. The first is called Fade01, and it animates the alpha property on a canvas group from 0 to 1. And it has the looping property set to false. The second is called Scale Pulse Point 1. It animates a RectTransform scale property from 1 to 1.1 and then back down to 1 again. It has the looping property set to true. My Fade Scale Animator controller has one layer for each of these animations and a default state assigned to that animation. When I play the project, you will see that the Animator component on the bottom bar game object plays both animations from the fade and scale layers. We see the objects fade in, and the scale pulse animation is on loop. You might also notice that because this is placed on the bottom bar, and we're using this particular RectTransform as the transform for the animation, the scaling is happening from this pivot point on the bottom bar game object. When we remove the Animator component from the bottom bar object and place it onto both the child elements, you will see that each child can utilize those same animations to fade themselves in and scale them up and down through the scale pulse animation. However, the difference is that each of these children is now using its pivot as the scale center point. So the animation is slightly different. When our UI elements need different combinations of animations, each needs its own Animator controller, which contains only the desired transitions for that controller. Here, I've created a new scale controller with only a scale layer and a scale state with the scale animation. I've assigned that controller to the Animator component on the red circle. When I play the project, we'll see that the red circle only uses the scale animation and not the fade animation. However, because they are still sharing this scale pulse animation asset, if I make changes to this asset, I can affect both controllers, both game objects and their animations at the same time. One final option is to create a master Animator controller, which holds all of your animation layers and corresponding clips. Here I have my master controller with a scale layer, the scale state, and the scale clip, and the fade layer, fade state, and fade clip. Then, to choose only a specific subset of these animations, I've created Animator override controllers. I have 2 controllers, a fade only and a scale only. The fade only defines an empty clip to override the scale, and the scale only defines an empty clip to override the fade. This way, when I play the project, each override controller only plays the animations from the master that it wants, and it replaces the ones it doesn't want with an empty animation clip, thus giving me this different functionality. Because both of these animator override clips are still referencing the master controller, if I add a new layer to the master controller called rotate, give it a weight of 1, and add a new rotate animation to the master controller, both of the animator override controllers will automatically pick up that animation. This can be a useful way to add new animations for all of your assets, but it does mean that if you don't want that animation, you'll have to come in and apply the empty clip as the override every time you add a new kind of animation state to that master controller. And here I've added the empty clip on the fade only controller, and so the green square will only fade and will not rotate or pulse. The Unity Playables API is another powerful option for playing animations. You can call the API from your monobehavior scripts, making direct use of animation assets and bypassing the need for an animator controller. To learn more about the Playables API, check out the documentation linked in the description below. Congratulations on completing this episode of the Unity Foundations tutorial. For more practice working with Unity's UI systems, check out the Unity learning pathways linked in the description below.